we're trying to find a straight line that best fits the data that we have, but in order to do that, we need to define what we mean by best fit. For example, if we have a set of data like this, we can have any number of lines that approximate that data. But which one is the best? In this case, we're going to define best as the line that has the lowest cost. Now, the cost function is a measurement of how far off the line actually is. For example, we can measure the cost by measuring the distance of each point from the line, then adding that up. So if we have 5 points here, the cost in this case would be the sum of these green lines, which are the difference between the actual value and the point on the line, which is the predicted value. There are other ways to do this, but we're going to keep it simple. In fact, we could make a formula out of this. We could say the cost equals the sum of the absolute value of y minus the predicted y. In order to make sure we always get a positive value for the difference between the actual and predicted values, one common thing we do is to square the difference, as in the cost equals the sum of the square of y minus y predicted. We call that the cost function. So we can evaluate how close each line is by plugging it into this formula. You'll notice that these weights are very important in determining the value of the cost function for a particular line because they determine the value of y predicted. So because the cost basically measures the difference between the actual and predicted values, it stands to reason that the line that approximates the data the best is going to be the line with the lowest amount of that cost. To figure out what that is, we need to figure out what the least cost, or the minimum, is, and what weights are going to make the cost function give us that minimum. We're going to do that using a technique called gradient descent. Gradient descent is quite possibly the most important thing you can learn about when it comes to machine learning. It's a really important foundation underpinning a very large percentage of what you're going to do. So let's look at it on a conceptual level before we look at the math. Have you ever played a game of hot or cold? This is a game where one person decides what the other one's looking for and gives them clues. If they move closer to the object, they're getting warmer. If they move farther away, they're getting colder. So if you're the seeker and you know you're getting warmer, you keep moving in that direction. If you're getting colder, you turn around and go in the other direction until you're told you're getting warmer again. That's what's called a qualitative way of looking at solving the problem of finding an object. It gives you the general idea, but it's not specific. You can't really measure it. Another way to look at it is quantitatively. Let's say I told you that I was thinking of a number between 1 and 100, and I wanted you to guess what it was. After each guess, I would tell you whether you were too high or too low. It's kind of like hot or cold, but you can be more deliberate here. Now, 100 sounds like a pretty big range, but chances are the conversation would go something like this. So, with only 4 guesses, Sarah managed to figure out what number I was thinking of, even though it was pretty far to one extreme. Gradient descent works a lot like this. You make a series of guesses, and with each guess, you're trying to get closer to the actual value that you want. You're trying to decrease the cost, or the loss function. Now, if the number I was thinking of was 83 rather than 82, it might have taken a few more iterations to get to the right answer. But what's important here is that after every guess, Sarah knew which direction she needed to go in, so she would have eventually gotten there. In this case, if we were to graph the cost function, or the amount by which each guess is off, it'd be a pretty simple graph. There's an interesting trend in this function. On the left side, the slope is negative. In other words, the cost is decreasing as we move closer to the right answer. And on the right side, the slope is positive because the cost is increasing as we move away from the right answer. Right in the middle, at 82, the slope is 0. That's called the minimum of the cost function. That's what we're looking for, and by knowing the slope of the cost function at any particular point, we know if we're moving toward the right answer or away from it. Now, that's a really simple example, and because all the lines are straight, it's pretty simple to see exactly where the minimum is. But let's say we wanted to generalize this and figure out article shares based on article length using the simplified Mashable data. In this case, our cost function is based on the distance of each point from the line, but because we want it to always be positive, we'll square it. Remember, when you multiply a negative by a negative, you get a positive. So in this case, the shape of the line looks more like this. All right, now this is a really big simplification, but go with me here for a minute. Got a nice parabola there, and we want to find that bottom point where the cost function is literally at its lowest. Now, think of this as a ski slope, and this is a valley. Let's say you broke your skis and you wanted to get into the valley. You wouldn't go uphill, right? No, you'd want to find the path that took you downhill the steepest. Well, ignoring the possibility of falling down the mountain and breaking your neck and all that. It's a hypothetical mountain. In this case, it's pretty easy to see, but it works in 3 dimensions too. Here you'd want to find the direction of steepest descent and take that. And the size of your steps is something that you'd decide. Are you going to take large steps or small ones? At the beginning, probably large steps. Like when Sarah chose 50 in the Guess Our Number example, she was right in the middle. It was the biggest step she could take. But as you get closer, you'll want to choose smaller steps. This choice is really important, though, because if you choose a step that's too large, you might jump over to the next mountain. But if you choose a step that's too small, you might freeze to death before you get to the bottom. Okay, so that's the general idea. In the rest of this unit, we're going to see how exactly we make this all work. But before that, we need to know how to make all this data visible. We're going to do that with a tool called Matplotlib.
If you're enjoying this video, you'll be glad to know that it's just a small part of a much larger course that can be found on Manning's live video platform. Live video is host to a variety of courses for software developers and engineers, and features helpful tools like our interactive transcript and intuitive integration with our live books. For this course and others, visit livevideo.manning.com.